I can't do it.
Okay, it's fine. Go for it. Go for it.
Chem Daddy over here, let's smell more.
That wasn't me saying that. How about the Pi Day edition of Chem Daddy?
Yeah.
Right? Pi Day. Did you have a nice Pi Day?
Yeah,
No,
I
I
made pie for my family.
That should be a big deal. That's fun. Okay, so yesterday we were talking about an electron returning back down to the ground state from the second to the first energy level, and we got as far as calculating this, and the answer to the calculation is on the next slide. That return to the ground state is going to have an energy of 1.6 times 10 to the negative 18. We have that? Yes. There's something that's kind of funny about this sign. Now, the sign does have to be negative because an electron that jumps up has to gain energy, so the delta E would be positive. Any electron that falls, whether it falls to the ground state or even falls toward the ground state, is going to release energy, so its delta E has to be negative. Now, that energy that it's getting rid of is a photon. It would be a photon of a specific certain frequency or energy that comes off. And we can calculate what the wavelength of that light is. Now we have two equations, and we saw them before. E equals h nu, and C equals lambda nu. Remember seeing those yesterday?
Yeah.
I think you wrote those down. Yeah. Where the E equals h nu, this is a relationship between the energy of light and its frequency. If the frequency of light goes up, the energy goes up. It's a higher energy light. In this one, if the frequency of light goes up, its wavelength goes down. Because in this second equation, wavelength times frequency equals c, the speed of light. Did you write that one down? I don't remember if we had that one in our talk yesterday or not. But we know c, yeah, we talked about c, the speed of light, 3 times 10 to the 8 meters per second. And we talked about the units of each of these things. Lambda, the wavelength is measured in meters, how far one wave crest is from the next. And then the frequency is measured in the unit called what? Hertz. Right, hertz, Hz, for the symbol on that one. Okay, now, what I'm going to ask you to do next is see if you, with this electron jump from the second to the first energy level of a hydrogen electron, according to the Bohr model, could we calculate what the wavelength is of that light that was given off? So, this jump, second energy level to the first, we get that wave coming out. What is the wavelength of that light? And we can calculate it using this. Now, what I did to find this equation, it's pretty simple. I solved each of these for frequency. Let's see if I can fit it on here. Frequency equals E over H. And in this one, frequency equals C over lambda. Since these are both equal to frequency, I set them equal to each other and solved for lambda. Can you see that? So we have an expression for finding lambda. If we know the jump in energy, H and C are both constant values, so you just plug it in. Now, I mentioned something about the sign on delta E. Up here, it was clearly giving off energy, so the delta E has to be negative. You can't leave the delta E negative in this one, though. So I guess the way I would express this, you have to take the absolute value of delta E, because you can't have a negative wavelength. I guess you could. It just means the wavelength is leaving the atom. Would you mind if it was negative? It shouldn't be negative. Make it positive. We never deal with negative wavelengths. So would you take a moment? It's very simple. You just plug some numbers in. Calculate the wavelength of that photon of light. You remember what H is? I'll just write it up here. 6.63 times 10 to the negative 34th joules per hertz. And then the C value is right up here, 3.0 times 10 to the 8. I'm no Zumdahl. You know that very well. But yeah, in the book, I know you were reading about the speed of light. They use like 5 significant figures. They're so precisionistic, right? 2 sig figs is good with me. It's like 2.997. Give me a break. Just call it 3 and let's be done with it. Save the ink. Over the delta E. And I'm just making it positive. 1.63 times 10 to the negative 18 joules. And there's a reason I'm asking you to do this. What would be the wavelength of that light? Go ahead and yell it out. 1.2? No, 10 to the negative 7th, I think.
Oh, well, my calculators.
Don't blame the calculator. Oh, and I just wrote the unit. Did you get a unit for your calculation? What is the unit?
Meter.
It is meters. Yeah. Does this work out to meters?
Yeah.
It does, yeah. And the funny, I mean, the joules is easy to see. That cancels out. But the hertz is in the denominator, and the seconds is over here in the denominator. They're being multiplied together. But hertz is a reciprocal second, and that would cancel the seconds in that term, right? So, yeah, these terms do cancel out, and all we're left with is meters. Yep.
Wait, what's that? What's the number there? 1.2 times
What's up?
10?
This times 10, I don't know how I raised it, to the negative 7th meters. Now, normally, wavelength is going to be expressed in nanometers, especially if it's around the visible range. Nanometer, you know what a nanometer is? 1 meter is 10 to the 9th nanometers. A nanometer is 1/1000th of a meter. So how many nanometers would that be? It's about 122. I only had 2 sig figs on here, but if you had 1.22 times 10 to the 27, it's 122 nanometers. And my question for you, and it's kind of marred up now, is this light of that wavelength, would we be able to see that photon of light coming off when the hydrogen electron jumps from the second to the first? I have a spectrum right here. There's really 2 spectra. This top one is the overall electromagnetic, the light spectrum, including all those forms of light that we can't see. The visible range is this little strip right in the middle. Our eyes cannot see very much of the electromagnetic spectrum. We can't see radar waves or radio waves, microwave. We can't see X-rays. You know, like when you have the dentist take an X-ray, that is just light wave that they're shining on your teeth. But it's a high enough energy, your eyes just can't see it. Only the area in here can we see. So above violet, higher energy than violet is ultraviolet. Below red would be infrared. We could do a lot with that. That's for physics. Now, my question was, on the previous slide, that electron jump, would we be able to see that light? It has a wavelength of about 122 nanometers. And these are the wavelengths in nanometers here. And you can see the answer is no. The visible range of the spectrum goes from just below 400, 380 or so would be like the violet at the very end of it that we can see. And that goes up to about the mid-700s, where the red would be. And after red, you just can't see anymore. So that electron jump would not be visible in the spectrum. Some jumps, though, of hydrogen, the electron jumps, are visible. And the thing that I'd like to do next is this. I'm going to ask you to calculate one electron jump, what the wavelength is for one electron jump. Can I have these 2 rows? All of you, would you determine the wavelength for an electron jump for hydrogen using the Bohr equation from the 3rd energy level to the 2nd? Would you calculate that and figure out what the wavelength is? The middle 2 rows, would you calculate the 4th energy level jumping down to the 2nd? And then the last 2 rows over there on the far right, would you do the 5th down to the 2nd? What's the wavelength of light that would be produced of hydrogen with that electron jump? Matthew, I'm having your 2 rows that you sit in calculate what the wavelength of light is of an electron jumping from the 3rd to the 2nd energy level. When you get an answer, consult with people around you, and have one person come up and write the wavelength up here. What did you do with it? Did you send it in? You just told me what your grade was. I'll do the same. I'll check. testing a gas tomorrow. I'm so
Friday.
far behind. Oh my
Friday.
gosh. I'll probably just barely get it done by the end of the before break.
I don't think so, Beverly.
No, I think you're in the lead.
No, Katie's listening tomorrow.
Oh, okay.
I pushed my back, I don't know, I don't have a good reason.
Yeah. I could probably rush and do it next Friday, but I'll probably want to do it like the UDometer, more volume line,
Yeah.
and
Get
put
17
one the week after.
It's all good.
You guys do?
Yeah.
No one's
That
gonna-
only leaves us about 9 weeks though. to do
No one's
biggies.
gonna die.
Times 3,
You're not, you're a cancer.
Guess Kate Rainey would be proud of me because I'm a little slower.
Wow, as long as you're going slow.
I guess. Go ahead and then once you have agreed on your wavelength, go ahead and send somebody up to record it.
4.9 times 10 to the negative 7.
Yeah.
716.
Give the wavelength in nanometers.
What did you use for the negative 2 E? You negative 2.2.
So 488 or 89.
I only use negative 2, so I'm all sorry.
Yeah.
Isn't it equals to? I'll write
Yeah.
it. Do we write it?
Yeah, go ahead and put it up next to your.
Yeah,
Oh,
the
yeah.
extra one's negative 2.1.
Wait, yo, I got 8. What did you get? Wait, did you use 2.1?
Nice.
You had it? Okay, me too. I got, yeah. You didn't say nice to me.
Jeff.
This is what mine
Yeah.
Why one
Oh, yeah.
It's just 1 over 1. These 1 and this 1. We're at the first one. Oh, that's 3. Never mind. You're right. Hey, Nathan, what did you use for the number? But it only changes.
Or these magnetic?
2.1.
Cool, isn't it? You don't normally get to come up and write on the smartboard in the other classes?
No.
We have to do this more often. I had added something to my one of my slides earlier. I'm going to jump back to it. The very first slide that I had with Niels Bohr with this picture on it, I went and added something to that, and I want to take you back. Whoops, I went too far. Check this out. I had totally blown this off yesterday, and I realized it when I was presenting it. I thought, oh, I need to fix that. So sorry that I blew this off, and you may have noticed that it was kind of absent. When I said Niels Bohr, the first thing I said about Niels Bohr was Niels Bohr observed the emission spectrum of hydrogen. I didn't talk about what the emission spectrum of hydrogen is. You just kind of wrote that down, and it was blown up. This would be an emission spectrum of hydrogen, and then 4 other elements. If you heat up hydrogen, and we analyze, we separate the colors, or we separate the hydrogen light into its colors, you won't see a nice continuous rainbow of colors like you would when you look at a white light. Like if we shine a white light through a prism, you get this beautiful rainbow all connected. The colors are connected. The emission spectrum of a specific element would not have a whole spectrum. It would have just a few bright lines. That would be the emission spectrum. So when Niels Bohr looked at hydrogen when he was heating it up, he would have seen 4 lines. There's a line there in the red. You can see that. There's a teal line. Whoops, a teal line. There's a purple line. And then there's one more. I don't know if you can see it. I'm kind of pointing at it. Do you see it? Hard to see. It's a deep purple color. Right there. Now, here's what I want you to notice. When we just take this and go back to what you just calculated, here, keep these wavelengths in mind. When the electron jumps from the 3rd to the 2nd energy level, we'll get a wavelength given off of 657 nanometers. Whoops. Now check this out. Here's the visible spectrum kind of exploded out. 687.